All right. So my name is Scott Stoltz. I'm a founder at Open Source Connections, and I'm very privileged to introduce Simon Hughes. He's the chief data scientist at DHI. I'm sorry. Excuse me. I'm going to read this. Simon is currently the chief data scientist at Dice.com, the technology professional recruiting site. He is also a PhD candidate at DePaul University, studying a PhD in machine learning and natural language processing, which he hopes to complete this year. How's that going?
Good.
Okay. At Dice, he has developed multiple recommender engines for matching job seekers with jobs, as well as optimizing the relevancy of both Dice.com's job and talent search, and more recently worked on Dice's Career Path Explorer and salary prediction tools under Career Explorer on www.dice.com.
Can you hear me? All right. Can you hear me at the back? All right, good. All right, so I'm here to talk about searching with vectors, or vector search. I'm basically detailing some initial POC we did about 6 months ago for how we can take an embedding model and scale it in our search engine. There we go. I'll also talk a little bit about vector-based models and embedding models in general, and how you might want to learn them and why, and how that works. Okay, so I'm the chief data scientist, and we work on job search and talent search for Dice, which is a technology job site. Rest of that you know, so I'm going to skip that. Why am I here today? What am I talking about? Well, recently we had this need to build a matching engine, where we match a job to a profile. And to do that, we decided to leverage an embedding model, a deep embedding model. So we have a document, we convert it to a vector, and then we use the similarity between different vectors to compute a score. We want to be able to scale that vector-based model in our search engine. And our talent search has a large number of documents, millions and millions of documents. And so we can't just pre-compute those cosine similarities offline. We need to be able to scale it. And we don't want to use a completely different engine. We want to be able to use Elasticsearch to do that. Unlike e-commerce sites, we rely heavily on content-based recommendations, because the most useful information we have about our customers is our profile, the resume. We don't have lots and lots of purchases and so on that we can use collaborative filtering. So what we wanted for this engine was we wanted a semantic matching engine that went beyond keyword search, so it can do a sort of semantic level match, so it can determine if two terms are similar, not just if they're the same keyword. And to do that, we need an embedding model of some kind. There's a GitHub repo that goes with this talk, which has some Python scripts that implement a number of these algorithms and give you examples of how you can sort of take an embedding model and sort of vectorize it into a search engine. Okay, so I'm going to start by talking about why we need a vector representation. Then I'm going to talk about how we learn a vector representation. And then lastly, the main part of the talk, we're talking about vector-based search using an inverted index. This clicker is very spongy. All right. So as most of you know, if you're understanding textual data, you'll face a number of key problems that are dealing with synonyms, that are dealing with ambiguity or polysemy, dealing with hyponym, hyponym relationships, and just typos and acronyms and other similar things. So what we want to do is we want to get past working with strings and going to matching things, to quote Google's marketing documentation. So what we want is we want to take documents and queries and terms, and we want to map them from this sort of textual space into a concept space or a semantic space, where we have different concepts that include important sort of topics or areas from our domain, so that similar things map to the same topics and different things map to different topics. So how do we go from a string or a series of document to a set of concepts? Okay. So traditionally in machine learning algorithms, the way to represent a word to a machine learning algorithm is to use a one-hot vector. And what it is it's a binary encoding where you have a component in the vector for each word in the vocabulary. And you have a 1 in the column that corresponds to that word, and then the zeros for everything else. So this is a very sparse representation, right? You have 1, 1, 1, lots of zeros. And it has this property where if you have two different words, even if they're similar in meaning, they have completely different representations. You only have the same representation if it's exactly the same word, even if you do stemming or whatever, if it's the same stem word. What we really want to do is you want to get to a distributed representation. Now, this is a big thing that came out of the deep learning literature about 10 years ago. They started talking about distributed representations, where we want to have vectors for things where similar things have similar vectors. So we're going from exact matching to sort of more semantic matching, where we have degrees of similarity. And that is represented for machine learning model as a vector, as a dense vector this time, or as a sequence of real numbers that represent some concepts, some learned concepts about the thing that you're trying to match. So a nice property of this that we wanted to have, ideally, is that similar items have similar vector representations. And you can compute a similarity score between items by just doing a dot product of the vectors. And most machine learning algorithms work with vectors in some way, shape, or form. So I've covered why a vector representation briefly. How do we learn a vector representation for a word or a document? So context. All embedding models, all semantic models, or nearly all of them that I'm aware of, they learn the meaning of words through the context, meaning what words occur with that word in some kind of context. The context could be a sentence, it could be a document, it could be a fixed window of words. And varying that context can give you different features and different attributes and so on. So there was something called the distributional hypothesis, which was coined by Harris in 1954, where he said a word is characterized by the company it keeps. So this kind of ignores word order, and it just says basically what I just said, where a word's meaning in general terms is defined by the words in which it's used with. It's kind of a simplistic meaning definition because it ignores word order, ignores grammar and syntax. If you want to look at a more sophisticated definition, there's something called a latent relational hypothesis, which isn't really covered much these days, but I'm just mentioning it here as interesting aside. Just look at those kind of things. So bag of words approaches, or bag of n-grams, kind of fall into these different categories. We started with latent models, so LSA, latent semantic analysis, and LDA, which is a topic modeling tool. They take the context as a document typically, and they do some kind of matrix factorization, and they come down with a sort of a latent representation of the document that's dense and much lower rank than the vector space. And this gives you a semantic vector space model. Earlier versions of conceptual search or semantic search used LSA quite heavily. I know Doug and John have written blog posts about that, amongst others. Then word embedding models came along in the early 2000s. The guys in Montreal started looking at language modeling, and that work was then later built on by Word to Vec, which is probably more commonly known in the GLOVE model. So where we learn using a language model, which is a very simple linear model for predicting the next word that occurs in a sequence of words. They learn to represent words as vectors using an embedding space. This idea of language modeling is becoming very important in NLP, and you'll kind of see that leverage more and more in more sophisticated approaches as we go on. So those are word embeddings. Then following on from the Word to Vec work, some people who work on sentence or document embeddings, where the context is basically a document or a document in the word window. So doc2vec is one of these, which a lot of you have heard of. Do I mention the Microsoft one? There's also, I think I'll get to that later. So there's a number of models, paragraph2vec and so on, that try to take an embedding and learning it from a document, not just a word or a sentence. That's Word to Vec, I'll skip that. So the limitation of these sort of bag of word or bag of n-gram approaches is that It's a very shallow representation. The word embeddings are limited to the level of word or phrase. The latent models are document level, but they don't encode relational information between the terms. You're trying to use them to solve the synonym problem, but they're not really learning true synonyms. They're learning relatedness. So Trump and Clinton, or black and white, will have very similar vector embeddings because they occur in the same context, even if they have a very different meaning. And polysemy. It doesn't solve the polysemy problem, right? Which is a fancy way for saying ambiguity. If a word has 5 different meanings, it'll have one vector. So it can't adjust itself to those different meanings. This is a globally optimized model. It does not adjust itself to the local context in which the word is used. So how do we get beyond these kind of simpler approaches? Recently, as of last year and the tail end of 2017, deep language models started to become very popular and very successful. So remember, Word2Vec is a simple language model. And language model, again, given a sequence of words, will predict either a missing word or the next word in a sequence. A deep language model is basically a deep neural network, multiple layers, that is trained on a large corpus of information to solve the language modeling problem. Now, why you would use this in place of a simple model is it can learn much more complex relationships, such that it can learn what are called contextualized embeddings. So given a word in a sentence, it can adjust the vector for that word based on its usage within the sentence. So the same word in 2 different sentences can have appropriately different vectors based on how it's used. I have a picture of Elmo and Bert there because one of the first models that did this was called Elmo, and the LM is language model. And then Google, jumping on the train, built their BERT model, which is a transformer model. UML fits the OpenAI transformer, and the GPT-1 and 2 models are other variants of this. Some of them are recurrent neural networks, some of them are transformers. And all of these can be used for encoding sentences or in some case documents into a vector space. They can have challenges, however, in scaling. Right? RNNs don't scale real well. Convolutional neural networks tend to scale much better. This is a picture of how a deep language model may look, very simplified, where it's basically just taking a sequence of words and predicting the next word. It's using a bunch of recurrent cells to do so. Okay, so some embedding models for search exist, and some simple approaches I've talked about and other people have already talked about. So one example which I've talked about is sort of using word embedding approaches for search. So one approach you can do that's quite simple for taking word embeddings and embedding them in a search engine is you can just cluster those embeddings, so cluster the vectors using some clustering algorithm, and then create a synonym file that maps your terms or your words to those cluster tokens. So you have maybe 5 different phrases that are in the same cluster. You create an artificial token for that cluster and index it like any other token. And that's kind of a very simple way to take a word embedding model, embed it into a search engine with very little complexity and changes to your algorithm. A common approach for learning a document embedding from word embeddings is to take the word embeddings and to average them. Often a weighted average using the document frequency. The IDF score, the inverse document frequency, can actually work better. And a guy called Tommaso Teofil, I don't know if he's here. Is he here? No. He wrote this great book called Deep Learning for Search, and it talks about that in chapter 5. So I encourage you to get that book if you haven't read it. And what you find with a lot of these approaches that try to embed word embeddings or some kind of embedded model into the search engine is, in some cases, they can outperform BM25. But typically a combination of BM25 and an embedding model does better than anything else. So similar to how ensembling can improve in a machine learning model, in a ranking model, if you use a combination of BM25 and an embedding model score, that can often give you better relevancy than either in isolation. Presumably because they're learning very different uncorrelated scores. And when you're combining models, it tends to work best when those predictions from the models are very different and not very closely correlated. Some other embedding models for search that people have developed. So Microsoft worked on this dual embedding space model, where it sort of tried to learn both embeddings for queries and documents simultaneously. There's papers linked there. They found that it consistently beat BM25 and also LSA, which I mentioned. Also beat BM25 in terms of different IO metrics. The dual embedding space model was better than LSA, and then dual embedding space model, which is a mouthful, and BM25 outperformed everything else. So very similar set of results again. So if you're considering using an embedding model in your search, I wouldn't suggest you just throw away your BM25. I would suggest you consider using both, or whatever your scoring algorithm is. Okay, so now get to the crux of the talk, which is sort of vector-based search in an inverted index. Okay, so how do we get vectors into a search engine so we don't have to build something other than an inverted index? So we can use Elasticsearch or Solr or whatever to scale your search using vectors. So what do vectors look like compared to an inverted index? Well, so at the top there, a very short vector with 5 elements. It's just basically a sequence of real numbers. They can be positive or negative. And then they have a size, so the larger or more negative the number, the more important that value. They're dense, they're not sparse, so there's not lots of zeros. They're much lower cardinality than, say, an inverted index. The inverted index is very sparse. It's pivoted by term. Each term maps through a hash lookup to a posting list, and the posting list is list documents or document IDs that contain that term. I'm sure 99% of you guys know that already. The dimensionality, so if V is the vocabulary, then you have an entry in your posting list for every term in your vocabulary. And it's fast because it's sparse. You can't actually, I don't think there's a way to exactly equate the performance of an inverted index, because it very much depends on your data. If you have terms that are in half of your data set, then your inverted index is much slower than it would be otherwise. But its speed comes from its sparsity. So if you're going to do kind of vector-based searching and vector-based matching, you need to also have that sparsity if you want to get the same kind of performance gain. So how do you search with word embeddings? I covered this briefly. One simple approach is you can, at query time, take your query term, look it up in your word-to-vec model, for say, and then take the top terms and use that as query term expansion. You can use the cosine similarity scores as weights on those query terms, and you can use that in either boost query, so making sure the original terms still match, or just as a straight OR query if you're okay matching documents that don't include the original terms. Again, you can use term clustering instead, so you're mapping your query terms to a cluster ID and indexing that. And one thing that you might consider if you're doing that is you can run a clustering algorithm multiple times with different sizes for your number of clusters. So say you're running k-means, you could have a k of 100, 1,000, 10,000. And then you have basically very broad to very narrow clusters that you can then weight differently, or use TF-IDF to weight. So you can cover kind of both broad and very narrow matches. But what we really want to do, if you want to do vector-based search, is we want to do basically k-nearest neighbor search. We want to take a vector and scan across all the documents in our collection, ideally, compute a cosine score, and return the top matching documents to that. So what we're trying to do is do KNN search, but do it at scale. If you look at KNN, you say, well, it runs in linear time, which sounds pretty good, right? But if you have millions or billions of documents, then that's not going to be fast enough when you want, sub-second or 100 or 10 millisecond response times. So if D is the number of components in your vector, the size of your vector, and N is the number of documents, then brute force nearest neighbor search is linear in N and D, so the product of N and D. But if N and D is very large, that still may be too slow. An inverted index is typically sublinear because it makes use of the sparsity of the terms. It uses a B tree or distributed hash table to look up the terms, so it's order 1 lookup. iterates the posting list, and then re-ranks in log n time. So it's fast, hopefully. So how do we use the optimal, what is the optimal vector representation in an inverted index? This is somewhat of a philosophical discussion I've had with John Berryman, amongst others, as to what we think we should have to take this dense vector and try to represent it in a way we can search on it. We probably want a sparse representation because we need that for speed. For relevancy, we want a distributed representation because each document should be a collection of tokens, and ideally not a single token, where the tokens represent some semantic feature of the space, even if it's learned by the model. We want to have a distributed representation still. We want to preserve similarity. This is really important. So we're going to transform our vectors in a way that we can search on them. Those vector representations still need to be similar under the new representation as they were in the old. So two vectors that were similar in the dense form, if we tokenize them in some way, they still need to have the same similarity. This is one thing that we might want is a Zipf-ian distribution of tokens. I don't think I have a good way to prove whether this is true or not, but if you look at words and how they're distributed, they follow this sort of Zipf-ian distribution, where you have a small number of words that are very common and then a lot of words that are very infrequent. You can make an argument that we probably want to see a similar kind of distribution for our resulting tokens to get the same kind of relevancy we get in regular search. Please talk to John about that because he has a good take on that. So Zipf-ian distribution. So what we want to do here is approximate nearest neighbor search. So we basically want to approximate full nearest neighbor, but we want to get it much faster. So to take that speed up, we're probably going to take some loss in accuracy. So it's really coming up with an algorithm that allows us to trade off speed or accuracy for speed and still get good results. Approaches to this can be either data dependent or data independent. What that means is the data dependent approaches are kind of adjusting to your data so that you have some kind of model that learns from your data, and if your data changes, then you have to retrain this model. And then you have data independent approaches such as hashing, where it doesn't matter how your vectors are and what shape they are, you can just still use the same approach each time, which has some benefits. Some approaches to this, there's many. It's a very broad literature, so I can't cover everything. But some of the main ones that come up are the KD tree, which I think is similar to the thing that Doug was talking about last session. LSH, which you've probably heard of, locally sensitive semantic hashing. Heuristic methods, like a k-means tree, the random KD forest, which is a variant of the KD tree, and then this HNSW model, which you can read about. And there's a fourth approach, which is vector thresholding, where you're taking the vectors and you're manipulating them in some way, kind of very simplistically to sparsify them by using a threshold. Whatever approach you take, your similarity metric is key to choose the right algorithm. Particularly with LSH. So the LSH algorithm you use will very much dependent on the type of metric you are trying to, your similarity metric that you're trying to use. So you need to, ahead of time, you need to figure out what your similarity metric is, whether it's coastline similarity, Euclidean distance, Jacquard similarity. Figure that out first before you go any further. So KD trees. KD trees are a way to do brute force nearest neighbor search, but in sublinear time. So great, why don't we just use KD trees? The way they work is they do a sort of iterative partitioning of the space such that they maintain a sort of binary search tree that allows you to very narrowly map into vectors that are very close to one another. However, they don't really work for this scenario because KD trees only really work well for small vectors. Once your vectors get larger than, say, 50 components, their performance is linear, so they kind of lose all of their speed advantages. An interesting paper I've seen actually is someone using PCA to take the vectors, compress them down to like say 10 components, and then running a KD tree on them, which I think is an interesting idea. So one possible solution to this, although you're still kind of doing that outside of your embedded index. You can do approximate nearest neighbor search with a KD tree. You can actually limit the number of nodes it searches. But this allows you to get some speed up and some loss of accuracy, but it typically is outperformed by more heuristic approaches, such as clustering and such as like clustering algorithms. Okay, so the second one is LSH, locality sensitive hashing, something you're probably familiar with. This is used a lot in production environments to scale recommendation engines, where you're looking at matches for, you're doing like collaborative filtering on a large set of documents, large set of items. And people are looking at Jacquard similarity a lot of times, and they're using LSH to speed that up. So LSH gets us speed up by using hashing. Is kind of like clustering in a sense, without any kind of model. LSH takes items and maps multiple items into hash buckets. And it does so in such a way that the probability of getting a hash collision is proportional to the similarity of the items. So items that are similar are more likely to share the same hash bucket. So normally you don't want a collision when you're having hashing. But LSH is the opposite. It's saying we want to have collisions, but we only want to have collisions when items are similar, and allows us to sort of take these vectors and discretize them into some kind of discrete space that we can do fast lookup on. Min hash is probably the more, so LSH is a family of algorithms depending on the hash function. Probably the most commonly used one is the sim hash, which is for Jacquard similarity. If you want to do cosine similarity, there's an algorithm called the sim hash. And what that does is, so if you have a 50 element vector and you want to hash with 100 bits, you generate 100 vectors of the commonality 50 randomly from the uniform distribution. And then for each of your vectors, you multiply it by each of those 100 random vectors. And then you take the sign of the dot product. And if it's positive, you set a 1. And if it's negative, you set a 0. So that allows you to basically take a 50 element vector and code it into a 100-bit space, and gives you a hash signature for that item. So that's one way to discretize a vector space such that items that have the same hash signature should be very similar. It seems kind of counterintuitive, like why would a random vector actually help narrow down your space? But it's a very good intuition. No, that's not going to work because we have no internet. That slide, the paper that's linked to my slides, kind of has a very good visual intuition as to why this works. But basically, when you pick those vectors, you randomly partition your space roughly equal, so that two items that are very close together will fall into the same partition. So you can take the output of this hash function, which is a series of bits, a bit string, and then you can index that into your index. You may want to just take the whole string and index that as a single token, or you may want to break it up into bits, into like 5 or 10-bit strings, and then index that. And that would allow you to then do non-inexact matches using, say, minimum should match or so on. So that's one way that you can go from a vector to a sort of tokenized representation. This is a data-independent approach because your hash algorithm doesn't have to adjust to changes in your embedding model. However, it's typically outperformed by heuristic methods that do learn from your data, but are more kind of effort to maintain. So this is sort of a visual representation of how LSH works. So you have your real vector at the top, your dense vector at the top. You hash it into bits, and then you encode those as a string or as a sequence of tokens where each component in your vector has a separate token representing the difference of the 1 or the 0. So you would take the index of that component as part of the token, and then you would take the 0 or the 1 as the next part and turn it to a string and then index it that way. Or you could take, like I said, bit strings from that big string and then index those separately. So slicing this one hash signature into, say, 5 different substrings. Each of those is one way to solve this problem. Then you can compute Hamming similarity between documents by just looking at the 1s and 0s in that hash function, and that will give you an approximate similarity score. So you can use that to do your first pass, get your similar documents back, and then do a brute force nearest neighbor search on the top documents. So what we'll mention in most of these approaches is kind of like a re-ranking approach in that you have an approximation where you're getting, say, the top 1,000 documents using some approximation, and then you do exact nearest neighbor search on those 1,000. You either do that offline outside of your search engine, or there's ways to do it within the search engine. Okay, the next approach is the k-means tree. So this is a hierarchical clustering algorithm. It kind of runs k-means in a sort of top-down fashion to create a tree structure. There's a paper. This is implemented in the Flan library. So this is best illustrated by a diagram. So you start at the root node, and you define a branching factor, b. Let's say 10, right? So a branching factor is 10. We're going to take all our documents, or a subset of our documents, and run k-means, which is really fast, to partition our documents into 10 clusters, if our b is 10. We then take each of those 10 clusters and all the documents within them, and then rerun k-means, again with a value of 10 on each of those 10 clusters to get 100 separate nodes. And then that way you're sort of building a tree, and you just keep repeating that in a top-down manner until the number of elements in each cluster is less than your branching factor, less than 10 in this case. So that gives you the sort of hierarchical clustering. And k-means runs in linear time. It's one of the fastest clustering algorithms out there. So you can actually scale this pretty well. Now, obviously, the hierarchical k-means runs in slower time than that, but it's still pretty fast. So to implement this in Lucene, we can pre-train a k-means tree on a subset of the index if we don't want to train on everything. So we could take, say, 10% of our index, train a k-means tree on it using all the vectors for those documents. And then we can, for each document, we can then navigate that tree and figure out which nodes it maps to. So at each level, we'll have a matching node that is the closest cluster, and then we follow that down the tree. So that gives us a sequence of tokens, one token for each level in the tree, that we can take our document and we can index it with. And those tokens will represent different levels of matching. So that the higher levels on the tree will be broader matches, and the lower levels of the tree will be very specific matches, very close matches. And there's different ways we can query this representation. Our query comes in, we convert it to a vector using the same embedding model. And so one thing we can do is we can search our tree in memory. It's pretty fast, it's a tree structure. Find the closest tree nodes, leaf nodes, and inject those as tokens into our query, and then do matching on that using the similarity between the cluster centroids of those tokens, of those clusters, as our weights. So how close are we to the top, 10 clusters, and then create tokens for those clusters, and add those as sort of expansion terms with the similarity weights like we did earlier. Or we can create a re-rank query where we sort of re-rank. So that's one way to. So basically, we're querying a tree. We're finding the leaf level nodes that are the closest match to our query vector, retrieving those, and then we can do a brute force re-ranking using exact nearest neighbor. We can use a re-rank query, for example, in Solr, and do a brute force kind of vector match to it. Here we can. One thing that's really powerful about this algorithm is it allows you to trade speed for accuracy. Depending on the depth of the tree and the granularity of the clusters, you can do a really deep tree and have a very granular search that will be slower but more accurate. Or you can step backwards and say, look, I'm only going to search 2 levels deep, and I'm going to take some hit in terms of performance, in terms of accuracy, but I get a big speed boost in terms of performance. So you could even dynamically adjust this as query load changes as to how deep you search the tree, because that also determines how big your queries come back, and how many items you're going to match. And you can even maintain an index that knows how many documents match each of those nodes. So then you can try to do some smart analytics to determine like how big or match or not you want to do, even before you query the index, and how many documents you want to come back. And the tree nodes roughly follow a Zipf-ian distribution, where you have the items at the top that are very common in lots of documents. And as you go down the tree, you get rarer and rarer tokens, rarer nodes in your tree. And so they follow that kind of Zipf-ian distribution we talked about. There's some sort of Lucene implementation details. I'll skip over that. But basically it comes down to each node in your tree, you assign a number to it, a unique number, and then you just index that as a token in your index. And then when you do matching on those tokens, you want to turn off a lot of your regular similarity scores because you just want to do kind of exact matches. And the only thing you maybe want to include is a similarity between your query and those clusters as weights at query time. So there's different ways to index this. This is how I did it. I have one field that has all of the nodes in it called clusters, and then I have a separate field for each level in the tree. And now each of these has a single node for a single value for each level, and then you can just do very fast lookups that way. Okay, some other heuristic methods. So the randomized KD forest is one that comes up a lot. I'm not clear on how you would implement that directly in an inverted index, so I haven't covered it here. There may be smart ways to do it. But basically, you construct a number of KD trees at random using a random subset of your vector, and then it searches all of them in parallel. But yeah, I'm not sure if there was a way to do that efficiently in an inverted index. There's this hierarchical navigable small world graph, which also is a very hierarchical model, but it's way too complicated to explain here. It's a graphical model. The paper is linked there. That had the best performance in some of the benchmarks I read. It's possible as it's a graphical model that you could implement that in an index, but it was more complicated than I wanted to look into. But it's probably, if you really, really care about the accuracy and performance, it's probably worth reading that paper. So the last approach I'm going to discuss is sort of vector thresholding, is what I would call it. I don't know if this you might not get search matches for that. I've only seen a couple of papers about this. They may call it something different. But basically what this is sort of motivated by is if you take the values of your vectors, your components in your vectors, and you plot them on a normal distribution, you'll see it on a chart, you'll see it has a kind of a normal distribution where most of the values are very close to 0. It has a mean of around 0, and there's only a small number of values in the tails. So because these are the values of the components of your vectors, and you're computing a dot product by multiplying them together, anytime one of those components is close to 0, the part of the dot product that corresponds to the component in the other vector will also be close to 0, because the number, if 0.9 by 0.1 is still very close to 0.1. So if one of the values is close to 0, both of them will be. So what that means is you can actually get rid of those values because without really impacting the cosine similarity. You can actually drop most of your vector components by just setting a size threshold. If it's close to 0, I'm going to drop it. Otherwise, I'm going to keep it. And that means your size of your vectors actually changes very little because most of the weight of the vector, most of the size of the vector is in a small number of components because it has this Gaussian distribution. If it had a uniform distribution, this wouldn't work. But because it has this Gaussian distribution, you can kind of drop most of the 0 elements. So how this looks. So the paper I read came up with this approach, which I actually don't like, but I'll explain it. So what you do is you take your vector, you pick the top 2 components in this case, those in bold. You drop all of the rest of them, set them to 0. So basically those don't become tokens in your index. And you take the last 2 components, you kind of round them to a smaller precision, and then encode them along with their position in the vector as strings. So the plus 0.63 became 04, because that's the index in the vector, plus 06, because it's positive. And then the second one became 07 minus 05. So this gives you one way to tokenize a vector and make it sparse. Now this has a lot of problems, right? So if I have a vector that's 0.05, that will have, an element that's 0.5, it will have a completely different match to 0.6. It will be as dissimilar as if it was minus 0.5. So it's kind of ignoring the numeric component and saying, okay, if you're within 0.1 of me, I'm going to match you, otherwise I'm not. So it's this. They claim to get reasonable performance with this, but it is a very kind of rough approximation of what you really want. So looking at this, I thought, well, maybe there's a better way to do that. I've messed around with payloads a lot. Instead of turning that into a string and losing all that numeric information, really, we can do something different. We can actually encode that value as a payload instead. So then we can keep all of the precision we had originally, and we don't have to do string matching when we want numeric matching. So instead you take your vector, you drop all the smallest elements, and then you take the remaining tokens, you only index those, and then in those you embed a payload, and that represents the value that you had for that component of the vector. And to query this, you can write a custom query parser that basically takes your query, converts it into a vector, and then does the same thing. But instead of payloads, we don't have payloads at query time. We can use the term boosting in place of the payloads. And then you want to write a custom similarity class that is able to also look at the payloads and influence the score. So it's relatively simple to do in something like Solr that's very plugin friendly, and it's probably doable in Elasticsearch with some work. Okay, so this is all POC that I did about 6 months ago. So I don't have access to production hardware. Andrew wouldn't let me do that. It's because our production hardware is very expensive. So I thought, I'm just going to run something on my laptop, and it's nothing like production, it's not distributed. But if I get I'm not going to be able to know how fast this is going to run in production, but the speed up I get, the relative performance of the algorithms should be roughly equivalent whether I'm running it on a small single node cluster or a large distributed cluster, with the caveat that it doesn't simulate the distributed nature of the cluster. Okay, so I took Solr 7.5 with a single shard and indexed 700,000 documents. And I took 1,000 sample queries, converted them to vectors, and then searched them against that index. Requests were single-threaded. My metric of choice is precision at 10. So it is very easy to actually benchmark this and actually determine how well you're doing. What you can do is you can do brute force search against your vector space, right, offline, and then figure out what the matches you want to get if you're doing slow brute force search. And then you can use that as your golden labels to determine the relevancy of your approximation algorithm. So you can compute what are the top 10 results I get using a costly brute force approach, and then if I use my approximation, how many of those 10 results do I get back using the approximate approach. I have results posted on the GitHub page, but I'll go through them briefly. What we get if we run those different algorithms with different settings is this rather ugly chart. It's not pretty. It doesn't give you nice sort of curved graphs or anything. But what this chart shows is basically to the top right is better, right? So when we're doing this approach, again, we're trading off speed for accuracy or relevancy. So on the bottom, we have recall. So 0.1 on the right, which means exact match to exact nearest neighbor. And then we have throughput on the y-axis. So the higher the throughput, the faster it's running, the smaller time, the less time the queries are taking. So we found LSH. I found LSH to be the slowest. That's the green bar at the bottom. Then the first vector thresholding method that we discussed, where they just stringify the elements, is the red one. So I got some good speed up there, but the accuracy was still pretty poor. When I flipped to the payloads, which was my idea, I'm assuming other people thought of that, but something that occurred to me. The purple line shows almost straight improvement in accuracy, but without any loss of speed. And then on the top right, we have the KD tree, which was the best sort of trade-off in terms of speed and accuracy. So the blue line, which is the best, is where I trained the KD tree on the entire index. Right, but that's not really realistic for production. You're not going to have a KD tree that you're constantly training as you're indexing new documents. So instead, to be more realistic, I took about 10% of our index and I trained a KD tree on that, and then used that to index everything else. And that was the orange line there. So I lost some accuracy by doing that, but that's probably more realistic in terms of production. I still got a good performance kind of accuracy trade-off. So here are the kind of numbers I was getting from Solr. So LSH I was getting a very low precision, and in queries was still taking over a second. The KD tree I was getting precisions of 0.8, 0.85, and about 9 or 10 queries a second, so 100 to 200 milliseconds response time. When I used the vector thresholding optimization, I was getting good accuracy again, but my throughput was very low. And then I used the payloads, so I got a big bump in accuracy, and then it took about half as long. I'm not quite sure why that was so much faster, but it was. The ultimate solution here is this idea of sort of sparse coding. also called dictionary learning. As what I think what we really want is a model that can directly learn a discrete representation, so we don't have to have two models or two approaches. And you'll see that in machine learning again and again. If you can take some complicated set of models and replace them with a single model that does everything, it tends to do better. So ideally, I think what we want to do is we want to have a model that can learn an embedding in a discrete space, right? That will directly learn embedding that you can use directly. You don't have to transform it in some way. There are some algorithms that do this right now. One is a sparse autoencoder, which is kind of a deep neural network that can learn to encode information in a lower dimensional space, kind of like LSA. There's KSVD, which is a variant of the SVD matrix factorization algorithm. Both of those can sort of take a vector and learn a sparse representation. But really what you want is an embedding model that can do this end to end. Some other approaches that are relevant, there's this word to bits paper where someone took word to vec and then tweaked the algorithm so it learned a binary string rather than a dense real vector. So that's a kind of interesting idea. So it learns kind of a binary quantized word vector. So I encourage you to look at that just out of interest. It might be useful. And then I recently learned about this sort of weak AND concept that they're putting into Lucene and Elasticsearch. Now, while this doesn't apply direct to vectors, as most of these approaches still generate very large queries where you have a large OR of tokens in most approaches, I can imagine this could be very useful to help speed up those kind of queries. So what this BlockMax WAND, I'm not sure if I'm saying it right, WAND, algorithm does is it's if you don't care about the number of documents you get back, and you want to do a big OR query, you say, give me the top 1,000 documents. It will selectively prune items from that disjunction as it goes along when it realizes that any documents matching those will not hit the top end relevancy score for your query. So it's basically a very fast way to do an OR query by kind of andifying it in some ways. And the speed up can be between 40% to 13x. Depending on your data and your queries. And so this might be useful in conjunction with some of the ideas I've talked about here, where you're generating large queries and trying to scale them. And that is the end of my talk. Thank you very much.
Thank you, Simon.